Perfect. So thank you very much, Peter, for the introduction. And thank you very much, everybody, for being at home or at work, attending my presentation. It's a very nice pleasure for me to do this presentation today. So my name is Dobrowolski. I'm a research assistant in Peter Skorba teams and at ZHAW. And what I would like to present to you today is a dynamic transmission system emulator for stability assessment. So let's start with a quick introduction. So because of digitalization, industrialization, urbanization, the power consumption is growing and growing every year. And this explains why the interconnection and the distances between generators are also increasing. However, more elements attached to the system implies that group of generators can, let's say, react adversely, causing the so-called inter-area oscillation. Inter-area oscillation are characterized by its low frequency, so usually between 0.1 and 1 Hertz, and its low damping ratio. So what you can see here, can you see my mouse, Peter?
Yes, it works.
Okay, so what you can see here is what happened in Europe the 1st December 2016, following an expected trip of a line between Spain and France. And what we can see is that in Europe, we have, let's say, 3 groups of generators, one in the western part, so with Spain, one in the eastern part with Turkey in blue, and let's say one in the center with France and Germany. So to control this oscillation, many solutions have already been proposed, from the tuning of existing control, usually power system stabilizer, to the design of a new control chain, so with wide area damping controller, so with the measurement of a complete area and the control of a complete area. One problem is that since we are talking about transmission grid, this control can be tested only in simulation, potentially in controlling the loop, in real-time simulator, but unfortunately it seems difficult to test control solution on a real experimentation. Just to give you a quick overview of the kind of models that we have for transmission stability, we have model from, so we have some very big model. I think this one is the biggest one, so the European model, the so-called ENSOI initial dynamic model. So with more than 6,000 generators, 23,000 buses, 7,000 loads, and 3 or 4 areas. So this model represents the European model. We have some, let's say, more simple model with the New England model, for example, with 10 generators, 39 buses, and 2 areas. And we have the smallest representation of a transmission grid with 4 generators, 11 buses, 2 loads, and 2 areas. So that's the so-called Kundur 2-area model. So this model will be the interest of this presentation. So yeah, and you will understand why. So let's have a quick overview of the outline. So I will first present you the Kundur original model, then how we scaled it in ZHAW laboratory, and I will present you some results, some perspective, and then do a conclusion. So let's go. Let's start with the Kundur original model. So the Kundur original model is the smallest representation of a transmission grid. It has 4 generators of 900 megavolt ampere each, lines of 25 kilometer, 10 kilometer, and 110 kilometer, 2 loads and 2 area. And what is very interesting with this model is that it represents what we want to see. So it represents some inter-area oscillation. So here you can see the result of a simulation when we trip the line between bus number 7 and bus number 8 here. And when we do a model analysis of this simulation, we can see that the mode number 3 is typically the inter-area oscillation with a frequency of 0.5 Hertz and a very small damping ratio. So, of course, we cannot represent this model in our laboratory. First, because you can imagine that 4 generators of 900 megavolts ampere is not possible. And of course, the second reason is that we don't have a laboratory of 300 kilometers. So what we did is that we mainly use a subsystem from Lucas Nuller, the company Lucas Nuller. So Lucas Nuller provides us a generator of 1 kVA and lines of, or represent, let's say, emulation of line of 25 kilometers, 8 kilometers, and 150 kilometers. And the line of 150 kilometers has been especially designed for us. One more important thing is that here what you can see is the typical generator. So we have the synchronous machine and the prime mover. And what we did in our laboratory is that we added a second prime mover to emulate inertia. Why? Because of course, a generator of 1 kVA doesn't have the same inertia of a generator of 100 megavolt ampere. So this solution gives us the possibility to increase the inertia. So this is the final implementation of our laboratory. So what you have to know is that for every generator, we have one AVR from ABB, so the unit roll 1010, and one unit roll 1020. We have one PMU measurement per generator, and we designed a turbine controller through Lucas Nuller PLC. With the, okay, so turbine controller, primary frequency control, secondary frequency control, but okay, this is not that much important for this presentation. So that's what you have to know for this presentation. Let's have a look at some results. So how I will present it to you, what you will see in every slide of the result is one video of what happened in our laboratory. So I'm here in gray, and this is Daniel Baltensberger in dark. He was my master student who worked on this project. You have here the PMU measurement, and what you can see here is the setting of the Kundur system. So for example, here, the first test is without any inertia. So we have the Kundur representation with generator of 1 kVA and no inertia, no additional inertia. So what I will do here is that I will increase the load in area 1. So that's what happened here. Then Daniel will increase the load in area 2. Sorry. And what we can see is that here we have a typical behavior without any inertia. So we don't have any inter-area oscillation. We don't have any oscillation actually. So the system is reacting really fast. And here we will do the zoom. And we have the typical behavior without inertia. So let's now add some inertia. So exactly the same thing, the same test, but with inertia. So we added inertia in all the generators. Oh, maybe something that I completely forgot to say is that all the color here in the PMU measurement corresponds to the color in the setting, of course. So what we can see here with the first load impact is that we already have a small inter-area oscillation. We can see it here between generator, so the blue generators and the yellow generators, so between area 1 and area 2. We have exactly the same thing here between the red one and the green one. So already when we added some inertia, we have some inter-area oscillation, we have some typical transmission grid behavior. So we can do a zoom again and we can analyze it on this picture. And the most representative test that we can do is that we can trip one line. So exactly as I showed you for the simulation when I presented the Kundur original model, we can trip this line during a power flow from area 2 to area 1 of 200 watts. So this just means that this load is consuming much more than this one. So we have a power flow of 200 watts here. So what I will do is that I will trip this line here. So when I will click on the button, takes a little bit of time because Daniel was a little bit scared of it. I like to say that he just told me here, I don't want to do it. So I trip the line here, so exactly this line. What we can see is that we have a very nice inter-area oscillation here between both yellow and green generators against the red one and the blue one. And when I will reconnect the line, we will also see a very nice inter-area oscillation. So actually the same one, but a little bit bigger. And so exactly what we want to see. The only thing is that this inter-area oscillation is a little bit, or is damped quite fast, but we have a very nice behavior. So when we do the zoom here again, we can definitely see that generator in blue and generator in red are reacting together, but against the one in yellow and the one in green. So of course, we have some other result. I can show you some other result, but I don't have time today. I will, during the conclusion, I will just give you an overview of all the tests that we can do. So just to give you some perspective, so as I told you in introduction, what is very interesting for us now is that we want to test some controls that we already designed, so some PSS implementation or some wide area damping controller implementation. For the PSS, something really good is that with the AVR from ABB, we have the possibility to design our own PSS inside the AVR. So everything inside the Unitrol 1010. So this is something really good. And with this Unitrol 1010, we also have the possibility to have an external input. So like this, so to sum the PSS with an external input. So we have the possibility to design a wide area damping controller. So I wrote here on a Raspberry Pi, but we can do it with everything, with every PLC that we have. At ZHAW, we will use, or we are using a Raspberry Pi actually. So this is two very nice perspectives. So just to conclude, we implemented the Kunduz transmission grid model using mainly Lucas-Null system. We have the possibility to change inertia. We have the possibility to trip lines. We have the possibility to trip generators. This is another very nice test to do. We have possibility to activate or deactivate a secondary controller. We have possibility to change some gain in the control and to see how it reacts. So we have we have a lot of possibilities. And something really important is that we are able to represent inter-area oscillation as well as local oscillation. So this is a very good result for us because this was the main objective. So right now we have the possibility to test some controllers that we already designed in simulation. So some wide area damping controller approach that we already published. Some new PSS tuning approaches that we already published as well, and some feedback control. So anyway, but we have the possibility to test a lot of controller on a real demonstrator and not in simulation. That's all for me. Thank you very much for your attention, and I will be really happy to answer if you have some questions.